Okay, so basically we are starting with the chapter of relations. Introduction was already given to this in the previous year. Then too we'll try to understand few things over here. A is a set which has objects 1 and 2. Okay. B is a set which has objects A and B. A cross B. Okay. A cross B is nothing but Cartesian product of A and B. It is 1A, 1B, 2A, 2B. Similarly, we can also find out Cartesian product of B and A, that is B cross A. Okay, so that is A1, A2, B1, and B2. The Cartesian product you people all already know. Okay, so what is a relation? Relation is nothing but any relation. Let's say R1. The relation is nothing but a non-empty set of a Cartesian product. So here R1 can be a subset of A cross B, R2. R1, R2, these are relations. Okay, it can be a subset of B cross A also. Fine. It's a non-empty subset of a Cartesian product. Now within a Cartesian product, these are ordered pairs. These are ordered pairs. The first object in any ordered pair before the comma is the first component, and the second object is called as the second component. First object is also called as pre-image. Second object is called as image. And the group of or the set of all first components or the pre-images is nothing but domain, and the set of all second components, which is the images, is called as range. All these basics you know. So the point over here is relation is a non-empty subset of any Cartesian product. Okay. So let us understand the types of relations. There are two categories of types of relations. So the first category, types of relations. So first category, empty relation. Okay. Now, first of all, in the previous slide, I said that a relation is a non-empty subset of a Cartesian product. Okay. But then here I would like to contradict myself by giving an example over here. So example, A is equal to 246 and B is equal to A is equal to 246 and B is equal to 7, 11. Okay. Now R is a relation on this. Let's say R1 is a relation on this. R1 has ordered pair A comma B such that A belongs to A, B belongs to B, and A minus B is even. Okay. So R1 will, this was the descriptive form. We'll find out the roster form. A is coming from set A, B is coming from set B, A minus B is even. So 2 minus 7, it is odd. So 2 comma 7 cannot be a ordered pair. Okay. 2 comma 11 is 9. Difference between them is 9. That is minus 9, which is not even. 4 comma 7. Can this be an ordered pair over here for R1? Will you tell me? Yes or no? Over the chat box, you can reply. 4 comma 7 cannot be an ordered pair because the difference is -3. 4 comma 11, will this be an ordered pair? The answer is no, because the difference is not even. Likewise, 6 comma 7, the difference is -1, and 6 comma 11, the difference is -5. It's not even. So will you tell me, guys, will there be any ordered pair in relation R1? Will there be any relation ordered pair in relation R1? Yes or no? The answer is no. Okay, so it's an empty relation. So sometimes, there will be nothing, no ordered pairs in this relation. So that's an empty relation. Okay, next one. Identity relation. You need to know these definitions. Identity relation. So if A is 1, 2, and 3, A is a set of three objects, that is 1, 2, and 3. R1. Okay. R1, it's a relation on set A. So R1 is a subset of A cross A. Okay. R1 is a subset of A cross A. So R1 is 1, 1, 2, 2, 3, 3. Okay. R1 is 1, 1, 2, 2, 3, 3. So this is identity relation where every object will be paired with itself. Every object will be paired with itself. Okay. Now let's say R2. R2 is also a subset of R2 is also a subset of A cross A. R2 is also a subset of A cross A. Let me give an example. R2 is a subset of A cross A. A is 1, 2, 3. R2 has 1, 1, and 3, 3. Will you tell me, is R2 identity relation on A? Yes or no? See, the point over here is this object 2, it should be paired with itself. That is missing over here. So R2 is not an identity relation. Every object should be paired with itself. Each and every object. There shouldn't be any missing link. Okay. Let me take one more example. I'll take R3. Okay. R3 is equal to, now R3 is also a subset of A cross A. 1, 1, 2, 2, 3, 3, and 1, 3. Okay. So is R3 an identity relation? No, it's not an identity relation because see, all objects are paired with itself, but then this is an extra pair, 1 comma 3. 1 has to be paired with 1 only, and 3 has to be paired with 3 only. Due to this reason, this is not an identity relation. Okay. So the only valid identity relation will be this R1. Okay. I'm giving more examples so that there is no confusion later on. A is equal to A comma B. Now R1 is subset of A cross A and R1 is an identity relation on A. So will you tell me what is R1 then? It's an identity relation, huh? R1. It's on A cross A. So what will be the ordered pairs in R1? Specific are ordered pairs. I'm asking. Tell me guys. Waiting for your reply. What are the ordered pairs in R1? Hello, hello, hello. Are you able to hear me? Please, please revert. What are the ordered pairs in R1? Correct. It's only AA and BP. Okay. So this is the only identity relation on A cross A. Fine. Now the third type is universal relation. Universal relation. Okay. So if A is equal to 1, 2 and set B is equal to A comma B. So A cross B is equal to 1A. This is the Cartesian product. 1B, 2A, 2B. 2A and 2B. Fine. So universal relation. If R1 is a universal relation, it is exactly equal to the Cartesian product. They both are same. They both have to be same. It's not a subset. It should be entirely similar or same as that of the Cartesian product. So R1 will be 1A, 1B, 2A, and 2B. This is the universal relation. So in this particular case, the universal relation is a relation which is not a subset, but then it is entirely the Cartesian product. Okay. Even if one ordered pair is missing, it's not a universal relation then. I hope you have understood this. Yes or no? Okay. Now the second category of relations, category 2, types of relations. Category 2. Now this is very important for the entire chapter. Types of relations. First thing is reflexive. Second is symmetric. And third thing is transitive. Reflexive, symmetric, and transitive. Okay. Now reflexive, specifies A relates with itself, where A is an object in the set. Currently, you'll not understand this, just copy this. A relates to itself. Symmetric specifies if A relates to B is true, if A relates to B is true, then the reverse, B relates to A, is also true. Then the reverse is also true. Just copy for the moment. You will not understand this until and unless I take some examples. Okay. Yeah. And the third thing, if A relates to B is true and B relates to C is true, then A relates to C is also true. A relates to C is also true. Fine. Okay. So I hope everybody has copied this. I'll start with the explanation. This part is very important for the entire chapter, types of relations. I'll take some examples now. Okay, I hope everybody has copied this. So let's suppose A is 1 to 3. One second. Yeah, A is 1 to 3 and R1 is a relation on A cross A. R1 is a relation on A cross A. Is a subset of A cross A. That means it's a relation on A cross A. And let R1 is equal to, I'm assuming R1 to be 1 1 2 2 1 2 2 1. So first thing we will try and understand what is reflexive. We'll try and understand what is reflexive. Now reflexive specifies every object should relate to itself. A relates to A. A relates to A. Every object should relate to itself. So 1 relates to 1, 2 relates to 2, but then 3 comma 3 is missing. Therefore not reflexive. 3 comma 3 also should be there. 3 comma 3 also should be there. Okay. Yes, just give me a feedback. Have you understood this or not? Why it is not reflexive? Have you understood? Okay. Next. Symmetric. Okay. Now 1 comma 1 is true. Reverse it. This is for sure. Reverse it. Come on. What is the reverse of 1 comma 1? 1 comma 1. Just reverse it. Is this true? That means, is it a part of the relation? Yes. When you reverse this, it is still a part of the relation. Similarly, 2 comma 2. Now this is true for sure. It's there in the relation. Reverse it. 2 comma 2. Is it true? Is it true? Is it true? After reversal, after you reverse this ordered pair 2 comma 2, is it a part of R1? Yes. Okay. 1 comma 2 is true. Why I'm saying 1 comma 2 is true? Because 1 comma 2 is there in the relation. 1 comma 2 is there in the relation. Is the reverse true? Is it true? 2 comma 1. Is it a part of the relation? Yes. Okay. So there is not even a single ordered pair where it fails. Not even a single ordered pair where it fails. So what we are going to write? If A comma B belongs to R1, then B comma A also belongs to R1. B comma A also belongs to R1. Okay. Therefore it's symmetric. Therefore it's symmetric. Okay. Now let us understand transitive. In the same example, we have to understand whether it is transitive or not. Okay, now let us start with 1 comma 1 is true. 1 comma 1. It is true because it is there in the relation. So this belongs to R1. So the next ordered pair should start from 1. To check transitivity, the next ordered pair should start from B, A comma B. So create a link from B. So we'll check 1 comma 2. A, B, B, C. This link should be there. This also belongs to R1. This both are true. This is true. What does this imply? This implies A comma C also should belong to R1. So what is A? A is 1 and C is 2. A is 1 and C is 2. So 1 comma 2. Does this belong to R1? Does this belong to R1? Yes or no? True or false? Yes, it also belongs to R1. Fine. Therefore, it is transitive for this example. We have to check some more examples. We have to select the examples which are failing. Okay, like we did in functions for onto. We need to find out where it fails. Now let us take this example. 1 comma 2 belongs to R1 Anything starting with 2? Yes, 2 comma 1. 2 comma 1 also belongs to R1. These both are true because they are a part of R1. What does this imply? This implies 1 comma 1 should also, A comma C should also belong to R1. Is this true? Is this true? The answer is yes. So for this example also, nothing fails. Okay? Yeah. One more example. 1 comma 2, create a link from 2. So I'll take 2 comma 2. 2 comma 2. Okay? Both belong to R1. A comma B, B comma C. This implies what? 1 comma 2 should also belong to R1. A comma C. Does this belong to R1? Does this belong to R1? Yes. Okay. So these examples are just for understanding. We cannot explain each and every example. This was just for your understanding. But how we need to present? A comma B belongs to R1 and B comma C belongs to R1. Therefore, A comma C belongs to R1. Okay. Therefore it's transitive. Therefore it's transitive. Now in this particular problem which I've given it to you, it's reflexive, it's symmetric, it's transitive, all three. Do you agree with me, guys? This particular example, is it reflexive, symmetric, and transitive? Yes, it is falling under all three categories. So it is called as equivalence relation. If it is all three, it is called as equivalence relation. If it is all three, it is called as equivalence relation. Oh, sorry, it was not. I'm sorry, I didn't look on that. It was not reflexive. Sorry, because 3 comma 3 is not there, na, that we discussed. Yeah, so it was not reflexive. So it's not equivalence relation. I'm sorry for this. 3 comma 3 was not a part of the relation, na, so it's not reflexive. So it's not equivalence. Otherwise, if 3 comma 3 is also there, then it is all three: reflexive, symmetric, and transitive. Therefore, it is equivalence. Okay. While answering, just you have to give proper answer. I asked whether it is reflexive or not. Somebody said yes. Yeah, fine. I don't have the slide in front of me. Next one. Next example. A is equal to 1, 2, 3. Okay. R1 belongs to A cross A. R1 is defined as follows: 1, 1, 2, 2, 3, 3. Okay. And 1, 2, 3, 1. And let's take 1, 3 also. Now, first part, reflexive. Okay. Now there are three objects: 1, 2, 3. So all three ordered pairs are present: 1, 1, 2, 2, 3, 3. Okay. So is it reflexive? Yes, it's reflexive. Okay, all three are present. So A relates to A, and A comma A belongs to R1. Therefore, it's reflexive. Fine. Has everyone copied this? Yeah, symmetric. Okay, 1 comma 2, it belongs to R1. Reverse it, 2 comma 1. Does it belong to R1? The reverse also should be true. Huh? Does it belong to R1? No, it does not belong to R1. Even if one example fails, everything fails. Like onto functions. We did this in onto functions. Okay. See, 3, 1 opposite is already there. 1, 3. That's true. Okay. But then for 1, 2, it is failing. So it is not symmetric. Even if one example fails, the entire category fails. Okay. Now let us check transitivity. Third one is transitive. Okay. So let us understand few things. Let us make these pairs. 1, 1 belongs to R1. Create a link from 1. The next link from 1 is 1, 2. This belongs to R1. This implies what? 1, 2 should also belong to R1. Is this true? Is this true? Yes. Okay. Then 1, 1 belongs to R1. 1, 3. This also belongs to R1. A, B, B, C. So this should be same. This number should be same. So 1, 3. Does it belong to R1? Yes or no? Does it belong to R1? The answer is yes. Okay. Few more examples we'll take. We are checking transitivity, third part. 3, 1 belongs to R1. 1, 3 belongs to R1. This implies 3, 3 should also belong to R1. Is this true? Is this true? Come on, guys, please reply. Okay, so this also belongs to R1. This also belongs to R1. Therefore, see, is there any example where transitivity fails? Is there any example where transitivity fails? I don't think so. Okay, so it is transitive. It is transitive because there is not a single example where transitivity fails. So how are we going to present this? We cannot give examples, no? A failing example is okay, but in all examples are true. We cannot give this so many number of examples. So A comma B belongs to R1, B comma C belongs to R1. Therefore, A comma C also belongs to R1. Therefore, transitive. Therefore, it is transitive. Okay. Yeah. Some more examples. Now the entire chapter has this only. We need to check the reflexive, symmetric, and transitive. Okay. So just copy the example which I'm giving you. R1 is a relation defined as is a brother of. Okay. It's not a numerical example. It's logical example. R1 is a relation defined as is a brother of. So first we are going to check reflexive. Okay. Now a person a brother of himself. Why himself? Because in reflexive we check with respect to the object itself. Is a person a brother of himself? So it's highly incorrect logically, right? A person cannot be a brother of himself. Therefore, not reflexive. Therefore, not reflexive. Yes. Any doubts in this? Anyone? Anyone with any query over here? Second, we'll check transitivity. We'll check transitivity. A is a brother of B. If A is a brother of B is true. B is a brother of A. We need to check this. Is this true? Is the reverse, converse part of it true? A is a brother of B. So B is a brother of A. Is it true? Now in this case, B can be a male or female. In this case, B can be a male or female. But then A for sure is a male because A is a brother. So A is a male. So what is B? B necessarily is he a brother? He or she is a brother of A? No. So B can also be a sister of A. Hey guys, are you understanding this? Guys, please give me a feedback. Otherwise, it does not. give a signal to me whether you're understanding or not. So this may not be true since B is a male or female. So is it transitive, guys? Is it transitive? Is it transitive? No. Okay. We'll check. Sorry, this was symmetric. I'm really sorry. I wrote a wrong heading over here. This is symmetric. Reflexive, symmetric, and transitive. I'm sorry. Okay. So it's not symmetric. Fine. Let's go to the third part, that is transitive. Reflexive, symmetric, and transitive. So the second heading I had given wrong. It has to be symmetric. I wrote it transitive. Okay. So A is a brother of B. Now this is for sure. This is true. B is a brother of C. These two statements are true. It is supposed to be true. The end result, A is a brother of C. Is this true? Above two statements are true. The first two statements have to be true to check transitivity. So if A is a brother of B, B is a brother of C, is A brother of C? Come on, tell me, guys. What do you feel? This really does not require any explanation. So A is a brother of B. A is a brother of B. Please tell me the gender of A. A is a male. B is a brother of C. So what is the gender of B? Male. Okay. Now what is C? What is C? Male or female? What is C, guys? Come on, tell me fast, quickly. It is male. C is male or a female. So in that connection, is A brother of C? Is this true? Is this true? Yes. Therefore, it is transitive. Therefore, it is transitive. Okay. Yes. Any confusion in this particular problem? Any confusion? Fine. Next example. R1 is a relation defined as is a wife of. Okay. So first case, reflexive. So can that person be a wife of itself? Reflexivity says what? Object should be related to itself. So is a person a wife of himself or herself? No. A person cannot be a wife of itself. Therefore, Not reflexive. Not reflexive. Second one. We are considering only two genders, male and female. Symmetric. RSNT. So symmetric. Now suppose A is a wife of B. So A is female and B is male. If this is true, reverse it. B is a wife of B is a wife of A. Is this true? If A is a wife of B is true, reverse it. The reversed statement, is it true? The answer is no. Isn't true. This isn't true. Therefore what? Not symmetric. It's not symmetric. Now the third case is quite interesting. You will find it a bit funny as well. Just a second. We'll check transitivity. Okay. A is a wife of B. B is a wife of C. Let this be true. A to B, B to C. Okay. Now guys, tell me, is this practically possible to check this example? A is a wife of B, B is a wife of C. चलो ये तो ट्रू है, पहला स्टेटमेंट it is true. Can the second statement be true? To go further and check transitivity? Highly inappropriate. A is a wife of B, so B is a male. How B can be a wife of some other person? Okay, so we cannot really check transitivity over here because the two statements have to be true to check transitivity, so that the third statement is true. But then at a very initial level, the second statement is not true. So in this case, transitivity cannot be checked because this statement is highly inappropriate. So the cases where we cannot check transitivity, we have to declare it is transitive. It is transitive. Okay. Again, I repeat, if we are not able to check transitivity, okay, then it is transitive. Because the case does not fail. Why it does not fail? Because we are not able to check only. हाँ, check करके fail हो गया, then that is a different story. But then here we cannot check only. Fine. So it is transitive. Next. R1 is a relation defined on triangles such that R1 is congruent to. This is the relation. R1 is a relation defined on triangle such that R1 is congruent to. This is the relation, is congruent to. Reflexive. Suppose there is triangle ABC. Is it congruent to itself? Is a triangle congruent to itself? The answer is yes. So what are you going to write? A triangle is congruent to itself. Therefore reflexive. Therefore reflexive. Okay. Next, symmetric. Symmetric. Now suppose triangle ABC is congruent to triangle PQR. So let this be true. Now reverse this. Therefore PQR is congruent to ABC. Is this true? When I reverse the statement, is this true? Yes, it is definitely true. Therefore, yes, it's symmetric. It is symmetric. Yeah. Next one, transitive. Let ABC be congruent to PQR, be true. Let PQR be congruent to DEF, be true. Both the statements are true. So this pattern can be true in both the cases. ABC, PQR, PQR, DEF. Does this imply ABC is congruent to DEF? This also should be true in transitivity. But then does it imply? If ABC is congruent to PQR, PQR to DEF, is ABC congruent to DEF? Hey guys, come on, tell me, is it true? Yes. Therefore, ABC will be congruent to, or sorry, it should be DEF. Fine. Therefore, true. Therefore, it is transitive. Therefore, it is transitive. So this example, yes, all three categories are true. Reflexive, symmetric, transitive, all three are true. So it is called as equivalence relation. Equivalence relation. Therefore, it is called as equivalence relation. Okay. Next example. Acha, instead of congruent, if I write similar, will it be equivalence relation? Will it be all three? Reflexive, symmetric, and transitive? Instead of congruence, I'll just write similar. Hello, hello, hello. Waiting for your answer. Will it be all three? Reflexive, symmetric, and transitive. If it is similar to them. Instead of congruency, we'll check similarity. Any guesses? Yes, it is going to be all three. Reflexive, symmetric, and transitive. So this also will be a equivalence relation. Okay. Next one. R1 is a relation on lines or coplanar lines. Okay. On coplanar lines means on a single plane. On a set of on a set of coplanar lines such that R1 implies what? Is parallel to. Is parallel to. So this is the relation. The relation is based on being parallel. Reflexive. Now suppose there is line L1. Is line L1 parallel to itself? Yes. In this case, it will be coinciding, but then it is parallel to itself. True. Therefore, it is reflexive. Parallel lines have the same slope. Even if it is coinciding, it will have the same slope. Symmetric. L1 parallel to L2 is true. This is for sure it is true. Does it imply L2 parallel to L1? T means 2. L1 parallel to L2, it is for sure it is true. That's our assumption. But then as per the assumption, will the reverse be true? Yes, will be true. Therefore, it is symmetric. Okay. Third, transitive. Let L1 parallel to L2 be true. L2 parallel to L3 be true. So will this imply L1 parallel to L3? Is this true? L1 parallel to L3? Will it imply L1 parallel to L3? Yes. Okay. Yeah. Next example. R1, same on coplanar lines. It will be on coplanar lines such that R1 is perpendicular to. The relation is perpendicular to. So reflexive. Reflexive. L1 perpendicular to L1. Guys, does this make sense? A line, is it perpendicular to itself? Is a line perpendicular to itself? No. So this is false. This is false. Okay. Yeah. Symmetric. Let L1 be perpendicular to L2 is true. Now reverse this. L2 perpendicular to L1. Does this make sense? Does this make sense? If L1 is perpendicular to L2, then L2 is it perpendicular to L1? Yes. Therefore, it is symmetric. Okay. Now transitive. Let L1 be perpendicular to L2. Let it be true. L2 be perpendicular to L3. Let it be true. Does it imply L1 perpendicular to L3? Okay. So this is L1. It is perpendicular to L2. Okay. L2 is perpendicular to L3. So does it imply L1 and L3 are perpendicular? No. This implies L1 and L3 are parallel to each other. But then we require L1 and L3 to be perpendicular to each other. So this is false. This is false. So it is not transitive. So it is not transitive. Okay. Next, R1 is a relation on real numbers. R1 is a relation on real numbers such that R1 has A comma B. R1 has A comma B where A is less than or equal to B. Where A is less than or equal to B. Okay. Reflexive. Reflexive. A comma A. This implies what? A is less than or equal to A. Why I'm writing A comma A? Object should be related to itself. No, that's why. And as per this rule, A comma B implies what? A is less than or equal to B. So A comma A will imply what? A is less than or equal to A. Is this true, guys? A is less than or equal to A. Is this true? This is true. Any number is less than or equal to itself. Okay. So therefore it is reflexive. Okay. Symmetric. See, even if one example fails, everything will should fail. Okay. Now 2 comma 3 implies what? 2 is less than or equal to 3. Reverse it. 3 comma 2. This implies what? Let this is true. The first statement is true. It has to be true. In symmetric, the first statement is supposed to be true. In transitivity, the first two statements are supposed to be true. So now reverse it. 2 comma 3, 2 less than or equal to 3 is true. So is the reverse true? 3 less than or equal to 2 is false. Even if one example fails, the entire type fails. So it is not symmetric. Transitive. Transitive. Now let 2 comma 4 is true. We know it's true. 2 is less than or equal to 4. And let's say 4 comma, which should start with 4 na, to check transitivity. 4 comma 10 is true. Both the statements are supposed to be true. They are a part of the relation. Does it imply 2 comma 10 to be true? Is it true or false? Is it true or false? Hey, tell me guys, come on. Is it true or false? 2 comma 10 implies what? 2 less than or equal to 10. Is it true? Yes, it is true. Therefore, it is transitive. It is transitive. Okay. Yeah. Next example. R1 is a relation on, let's say, real numbers such that such that A comma B and C comma D belongs to R1. A comma B and C comma D belongs to R1. And A comma B relates to C comma D implies A plus D equal to B plus C. A plus D equal to B plus C. The meaning of A comma D relates to C comma D is A plus D equal to B plus C. Okay, something different. Reflexive. Earlier I was checking objects. Now I will check ordered pair. The ordered pair is A comma B. So the A comma B ordered pair should relate to itself. A comma B relates to A comma B. Now let us find out whether this is true or false. And A, B, C, D are real numbers. Okay. Now see guys, what is given to you? AB relates to CD. The meaning of this is sum of the extremes is equal to sum of the means. In that case, this implies what? Sum of the extremes A plus B equal to sum of the means equal to B plus A. By the rule which they have given in the problem, A comma B relates to A comma B implies what? A plus B equal to B plus A. Is this true guys? Is this true? Is it true? Is A plus B equal to B plus A? Yes. So this is true. This is true. Fine. So it's reflexive. Symmetric. Okay. Symmetric. Let A plus B relates to C plus D implies A plus D is equal to B plus C is true. This is the given rule. It has to be true. Okay. Now reverse this. Therefore, C comma D relates to A plus B implies what? Sum of the extremes. C plus B equal to D plus A. Is this true? Is this true? See guys, mathematically, if A plus D is equal to B plus C, if this thing is true, if A, B, C, D are numbers, then is C plus B equivalent to D plus A? Yes, this is also true then. Any doubts, any confusions? Any doubts, any confusions? Tell me. Therefore, it is symmetric. Therefore, it is symmetric. Transitive. Okay, we'll check transitivity. A comma B relates to C comma D implies what? A plus D is equal to B plus C. Now this is true. C comma D relates to E comma F. The first two statements are supposed to be true. So C plus F is equal to D plus E. So these two statements are true. Let this be 1, let this be 2. Add 1 and 2. Add 1 and 2. A plus D plus C plus F equal to B plus C plus D plus E. Some cancellations. C and D. C and D is getting cancelled. So A plus F is equal to B plus E. We got this result. Okay. Does this imply A comma B relates to E comma F? The meaning of this is this, yes or no? Sum of the extremes. Sum of the extremes is equal to sum of the means. So this box, does it imply this? A comma B relates to E comma F? Are both related then? Yes or no? Hello. Yes, they are related. Therefore, it is transitive. Okay. So with this discussion, I will end today's class over here. I hope everybody has understood the introductory part. Okay. Thank you.